Let's take a look at this paper. Question 1.1. Which one of the following pairs can be classified as scalar quantities? Now, in order to answer what scalar quantities are, we should know what our vector quantities are. Vectors are dam, VW, FM. So displacement, acceleration, momentum, velocity, weight, force, and magnetic field, or any field for that matter. So using this, we can then choose option A as our answer, because option A does not have any of these as options, meaning that those are scalars. Question 1.2. The vertical component of a force acting on an object moving horizontally, A, accelerates the object horizontally. So, okay, let's draw a diagram here. So I have an object, it's on a table, and let's say that it's moving this way. So its movement is that way. Now, the vertical component of a force, actually, let's do this. Let's make it a bit easier. Suppose we have a force applied like this. Now, that force is going to have two components. It's going to have a horizontal component, so let's call that Fx, and it's going to have a vertical component, let's call that Fy. Now, the horizontal component is going to be responsible for moving the object on the table. So horizontal motion. So A accelerates the object horizontally. That's not going to be the case because the vertical component is not going to move it horizontally. Option B accelerates the object vertically. So this thing is, whatever this is, it's moving on a table. The object is not moving upward, so it's not going to accelerate the object vertically, so that's going to be out. C has a tendency, so that sounds more or less correct, that word tendency, because it's not actually doing it, but it tends to do it. So it has a tendency to move the object vertically. That sounds correct because a vertical force will tend to move an object vertically. Or D has a tendency to move an object horizontally. That's out. So the answer is most correct is C. A force will tend to move an object in that direction. So vertical force will tend to move it vertically. A horizontal force will tend to move it horizontally. 1.3. A crate is moved from rest across a horizontal rough surface by a force F. Which one of the following statements about the kinetic friction acting on the crate is possible? So A says the kinetic friction is greater than the maximum static friction. So that's out, because if we consider the graph of friction, the graph looks like this, where this is Fs max and that's Fk. Fk is always less than Fs max. So A and B are out. Option C, the kinetic friction is less than maximum static friction, that is correct, and greater than F. So we have to consider, would the force be greater than the force applied? Will friction ever be greater than the force applied? So to understand that, if I have to draw an object on a table, and the object is being pulled this way, let's say with 10 newtons, that's the force applied. Does it make sense that the friction can be 11 newtons? Not really. Not really. The friction is there to slow the object down if the object's already moving. So it's going to be less than the force applied, D. And this makes sense because they tell us a crate is moved from rest across a rough horizontal surface by a force F. So it was being moved from rest and it has a force applied that is F. So that means that the force applied is definitely more than Fs max because it's moving, right? So if that same force is being applied on the object, it stands to reason that the force is still going to be greater than friction or kinetic friction. Question 1.4. Consider the following statements related to Newton's third law. When a force acts on an object, the reaction to this force acts on the same object. That's incorrect. The reaction to this force acts on a different object. That is correct. The time for which the force acts is greater than the time. No, that's wrong. In question 4, the force and the reaction to this force are in opposite directions. That is true. Which of the following statements is or are true? The answer is B. 1.4. The answer is B. Question 1.5. The acceleration versus resultant are drawn and they're asking which is true. The object X has a greater mass than object Y. So what we need to look for here is gradient. So gradient is Y over X. So essentially the gradient is the acceleration divided by the resultant force or F net. If we go to our formula, F net is equal to ma. So if I divide both sides by a, I'm going to have F net over a is going to equal m. So F net over a is equal to m. But we have the opposite. We have a over F net. So a over F net is going to equal 1 over m. So what does that mean in terms of the graphs? It means that the graph that has the greater gradient is actually going to have the smaller mass. So this has a lower mass. Because remember, the gradient is the reciprocal of mass. This has a higher mass. So object X has a greater mass than object Y. That is incorrect. Object Y has a greater mass than object X. That is correct. So the answer here is B. Question 1.6. The magnitude of the gravitational acceleration on Earth is g. What will the value of the gravitational acceleration be on planet X, which has the same mass as Earth but half the radius? So g is equal to gm divided by half r all squared. So now that can be expanded as a quarter r all squared. So there is an imaginary 1 here. So 1 divided by a quarter is 4. So 4gm over r squared, which is essentially 4g. So the answer there is B. Let's take a look at question 1.7. A small test charge Q is placed exactly halfway between two fixed identical charges carrying a charge of plus Q. The electrostatic force experienced by the test charge will be 0. So 0, the answer is C. That's because if you imagine this test charge as a positive charge, it's going to be repelled this way and it's going to be repelled that way. And because those charges have the same charge and because they are the same distance apart, the forces are going to be the same. So it's going to be pushed to the left, it's going to be pushed to the right with an equal amount of force, so essentially they cancel. Question 1.8. The minimum resistance that can be obtained by connecting two 4-ohm resistors in a circuit is what? Okay, so we can connect them either in series. So if I connect them in series, I'm going to have 4 plus 4, which gives me 8 ohms. Or I can connect them in parallel. So if I have them in parallel, I'm going to have R parallel is equal to product over sum. So 4 times 4 divided by 4 plus 4. So that's 16 over 8, which is 2. So the smallest I can get is 2. So the answer there, D. Question 1.9. The two resistors in circuit 1 are identical. They are connected to a cell with EMF V. The same resistors are now connected in parallel, shown in circuit 2. What is the power dissipated by each resistor in circuit 2? So in circuit 1, they are in series, and so the voltage is going to be half V here and half V here. Now because they're in parallel, each resistor is going to have V and V. So power is equal to V squared over R. Right? So this is in series. We can calculate it. We'll say in series, they are going to have a power of half V all squared divided by R. We don't need to do that. They're just asking for in parallel. So in parallel, we're going to say power is equal to V squared over R. And here we're just going to have P. Should we do, yeah, okay, let's just do series. So series, it's going to be power equals half V all squared over R. So that's going to simplify as a quarter V squared over R, which is a quarter P. So if in parallel they have a power of P, and in series they have a power of a quarter P, it means that in parallel it is 4 times the power that is in series. So the answer there, 4P, the answer is B. Question 1.10, a bar magnet is moved into and out of a solenoid. Which one of the following changes will result in a larger induced EMF in the solenoid? Using a weaker magnet? No. Using a solenoid with fewer turns? No. Using a solenoid with a smaller diameter? No. Moving the magnet faster into and out of the solenoid? The answer is definitely going to be D. And you could use the formula E is equal to minus N delta phi divided by delta T. If you are moving the magnet faster into and out of the solenoid, you are decreasing delta T, which means that the EMF will increase. Let's now take a look at question number 2. 3 coplanar forces F1, F2, and F3 of magnitude 6, 3, and 4 respectively act on an object. The sketch below, not drawn to scale, shows the directions of the forces. Question 2.2, calculate the magnitude of the resultant force acting on the object. Now this is worth 8 marks. So 8 marks tells me that we have quite a bit of calculation here to do. And with these questions, what you need to do is, you need to break up the forces that are acting at angles. So F1 doesn't necessarily need to be broken, F2 doesn't need to be broken, but F3 does need to be broken because it's at an angle. So let's just focus on that. So 2.2.1. Force F3 is going to have 2 components. It is going to have a vertical component, so F3y, and it's going to have a horizontal component, which is going to be F3x. So F3y is going to equal the force, so F3 times, now if you look at this triangle, F3y is opposite the angle. So the trig ratio that uses opposite and the hypotenuse is sine. So F3 sine 45 degrees. So F3 is 4. So 4 times sine of 45 degrees. And that gives us, give me a second, 4 sine 45 is equal to 2,83 newtons. Then we'll repeat for F3x. So F3x is going to equal F3. Now if you look at where F3x is, it is adjacent, so we will use cos 45. That's going to be 4 times cos of 45 degrees, which is the same thing, 2,83 newtons. Now to get the resultant, we need to add up all the forces in the y direction and all the forces in the x direction. So we call it the FR, the resultant force in the x direction is going to be, well, it's going to be the 2,83 plus, if we look at what other forces are acting in the x direction, we can see that F2 is acting in x direction. And because F3x and F2 are acting in that same direction to the right, we will add them. So plus 3, let's write that in. That's going to give me 5,83 newtons, and that's to the right. Then we'll do the resultant in the y direction. That's going to be, now F1 points upward and F3y points downward. So we're going to have to subtract here, right? So I'm going to choose up as positive and I'm going to say 6 minus 2,83, which is equal to 3,17 newtons, and that's going to be up. So to get the resultant, we can draw a triangle. So we'll have a force going this way, that's 5,83. We'll have a force upward, which is 3,17. So our resultant will be the hypotenuse. So we can use Pythagoras to solve this. So the resultant is going to equal, so r squared is going to equal 3,17 squared plus 5,83 squared, which is equal to, so we just square root at the end, 6,64 newtons. Question 2.2.2 says calculate the direction of the resultant force. So what we basically need to do here is we need to work out what this angle is. So it's simple, we can use tan. We can say that tan theta is equal to 3,17 divided by 5,83. Then theta is equal to 28,53 degrees, or so 28,53. And what direction is this? It is north of east. So why are we saying that it's north of east? Because imagine that is our east line. We are moving north of it, 28,53 degrees. We are moving 28,53 degrees north of it. Now let's take a look at question number 3. Question number 3 is about inertia. 3.2 says a passenger is seated in a fast-moving taxi when the taxi driver suddenly slams on the brakes. Use your knowledge of Newton's laws to explain why the passenger moves forward when the brakes are applied. So 3.2, so when the taxi is moving, the passenger, so I'm just going to write PASS, and taxi move as one system, right? And that basically means that they're both moving at the same velocity. When the brakes are applied, there is an F net that is slowing down the taxi, right? So the taxi slows. But the passenger is not necessarily feeling the brakes of the car. The passenger still wants to move forward, right? So the passenger's inertia moves the passenger forward. That's basically why the passenger moves forward. Question 3.3. Explain why wearing a seat belt is a safety measure for the occupants of a vehicle. So when the passenger moves forward, right, the passenger exerts a force on the seatbelt. Now, according to Newton's third law, the seatbelt is then going to apply a force on the passenger. So the belt applies a force on the passenger. And because of that, the passenger stays seated. Question 3.4. A crate of mass 80 kilograms lies on a rough plane inclined at 25 degrees to the horizontal. The crate begins to slip when the angle of inclination exceeds 25 degrees to the horizontal. The crate begins to slip. Okay, yeah, I've read that. Refer to the diagram below. Question 3.4.2. Draw a free body diagram showing all the forces acting on the crate. So 3.4.2, there's going to be weight, there's going to be a normal force, and there is going to be friction. Question 3.4.4, calculate the magnitude of the normal force. Now, this weight is going to have two components. It's going to have a W perpendicular, and it is going to have a W parallel. So the W perpendicular is going to equal the normal. So W perpendicular is equal to the normal force, which is equal to mg cos theta. That is, it's simple if you just remember it. So the mass of the crate is 80, gravity is 9,8, and then cos of the angle of inclination is 25 degrees, and that's equal to 710,55 newtons. Question 3.4.5. Calculate the magnitude of the maximum static friction acting on the crate. So friction is equal to mu s times Fn. But we don't know, we don't know friction. Okay, so they're asking for calculate the magnitude of the maximum static friction acting on the crate. So this is simply going to equal, so friction, instead of using the formula there, friction is going to equal W parallel. Because the system is stationary, it's in equilibrium, those forces are going to be equal but simply in opposite directions. So friction, instead I will equate it to W parallel, which is equal to mg sine theta. So that's going to equal 80 times 9,8 times sine of 45. And that gives us an answer of 331,33 newtons. 3.4.6, calculate the coefficient. So this one we can use the normal formula. Fs is equal to mu s times Fn. We know friction 331,33. That's equal to mu s times the normal. We worked out 710,55. Now you divide, mu s is equal to 0,466. There are no units for this, so we leave it as that. Question 3.4.7. If the mass of the crate is increased, will the crate begin to slide? Choose from yes or no, and explain the answer. So if we increase the mass of the crate, what is that going to change? So let's consider our free body diagram again. There's our component. There's our component there. So we have weight, we have Fn, we have Fs. So if we increase the mass, surely then that's going to have an effect on the weight. The weight is going to increase. Now let's consider what effect that's going to have on W perpendicular and W parallel. W perpendicular is mg cos theta, and W parallel is mg sine theta. If I increase the mass, it means that mg cos theta will increase. That means the perpendicular will increase. If the perpendicular increases, it means Fn will increase. Likewise, W parallel, mg sine theta will increase. It means that Fs should also be affected. So the answer here is no, right? So the reason is the W parallel, right, will increase, and that means the Fs max will also increase by the same magnitude. Let's take a look at 3.4.8. If the angle of inclination is changed from 25 degrees to 20 degrees, how would this change affect the static friction force acting on the crate? Choose from increase, decrease, or remain the same, and explain the answer. So again, let's go back to our free body diagram. Here we have Fn, we have Fs, we have, I'm just going to draw the components. This is W perpendicular, and this is W parallel. Parallel. So W perpendicular is mg cos theta, and W parallel is mg sine theta. So if we are decreasing the angle, what effect is that going to have on W parallel? So let's take a look. So a sine theta graph looks like this. If I decrease the angle, so say I'm going from there to there, sine theta gets lower. So if sine theta gets lower, it means that this whole value will get lower, right? So they want to know, how will this change affect the static friction? Since we know that the system is in equilibrium like this, we can say that Fs is equal to W parallel. Now if W parallel is getting lower, it means that Fs will also decrease. Okay? Let's now take a look at question number 4. Two blocks of mass 1 kilogram and 3 kilogram are connected by a light inextensible string. The blocks are initially at rest on a smooth horizontal surface. A force F of magnitude 9 newtons is applied to the 3 kilogram block as shown in the diagram below. Question 4.2. Draw a free body diagram showing the forces acting on the 3 kilogram block. So on the 3 kilogram block, we have a force applied. Because it has a mass, it's going to have a weight. It's on a table, so it's going to have a normal force. It's also going to have a tension force to the left. And Well, it's a smooth horizontal surface, so that implies no friction. Okay, so those are our forces. Question 4.3. By applying Newton's second law to each block separately, calculate the magnitude of the acceleration of the blocks. So we need to draw a free body diagram of the forces acting on the 1 kilogram block. So the 1 kilogram block is going to have weight, it's going to have a normal force, it's going to have tension. So I'm going to choose right as positive, and I'm going to apply F net equal MA. So this is simply going to be T is equal to 1 times A is A. Now I'm going to apply F net equals MA to the other block. So F net equals MA. So because force applied is acting at an angle, the horizontal force is what we're interested in. So the horizontal is going to be Fx. So Fx is going to be 9 times cos of the angle, so 9 cos 25, minus the tension, and that's going to equal 3a. So 9 times cos of 25 is 8,16. So 8,16 minus t is equal to 3a. Now we want to solve for acceleration, so it would make sense to make t the subject of the formula. So here I'm going to have 8,16 minus 3a is equal to t. So t is equal to t. So I'll have a is equal to 8,16 minus 3a. That means 4a is equal to 8,16. That means a is equal to 8,16 divided by 4, which is 2,03, well, 2,04 meters per second squared, and that is going to be to the right. Well, the question asks for magnitude, so we don't need to give a direction. Question 4.3.2, calculate the tension. So we know that tension from this formula is equal to acceleration. So if tension is equal to acceleration, it means that the tension is going to equal 2,04. So question 4.4 says the 1 kilogram block is replaced by a block with a bigger mass, while the force applied on the 3 kilogram block remains unchanged. State whether the tension will increase, decrease, or remain the same. Give a reason for the answer. So what's essentially going on here is that if you imagine this entire system as one thing, if you increase the mass of the system increases. And since the force applied on that 3 kilogram block is staying the same, it then means that it's going to require a larger force to pull it, but the force applied is not increasing, so that means the tension must increase. So tension must increase. Now there is another way you could look at it. If you look at the 3 kilogram block, right? So the 3 kilogram block has a formula. Well, tension is going to equal F cos 25 minus 3a. Now, as we said before, since the mass of the system is getting bigger, the acceleration must decrease, right? Now, since the force is staying the same, see this force here, it means that the tension has got to increase in order to keep this the same. Okay, let's move on to question number 5. Question 5.1, state Newton's third law. Okay, 5.2, differentiate between the mass and the weight of an object. Okay, this is quite straightforward. Mass is the amount of matter that's within an object, and the weight is the force at which the earth is attracting the object. 5.3.1, a 70 kilogram mountain climber reaches the top of Mount Everest 8.85 kilometers above sea level. Take the surface of the earth to be sea level. Okay. At the top of Mount Everest, determine the acceleration due to gravity. So we can use the formula. So 5.3.1 G is equal to gm divided by r squared. G is 6,67 times 10 to the power minus 11. The mass of the earth is 5,98 times 10 to the power 24. That's in our data sheet. And that's divided by, well, the radius. The radius of the earth is 6,38 times 10 to the power 6. And we are adding now, because they are above the sea, we are adding in 8,85 times 10 to the power 3. So we need to convert that to meters. So to convert kilometers to meters, you multiply by 1,000 or times it by 3. And not times by 3, times 10 to the power 3. And then you square that. That gives us a gravity of 9,77 meters per second downward. Meters per second squared downward. Question 5.3.2. Calculate the mountain climber's weight. So Fg is equal to mass times gravity. The mass is 70, gravity is 9,77, and that's equal to 683,90 newtons. Question 5.4. A learner makes the following statement. An astronaut orbiting Earth experiences weightlessness because he or she is beyond the pull of gravity. Is the statement correct? Answer is no, the statement is not correct. Okay, explain the answer. So what the learner is stating is that when the astronaut is in space, they do not experience gravity at all. That's incorrect because they are still in that gravitational, they are still going to experience the force of gravity on the earth. It's just that the distance now is going to be very, very small. So it's not going to be zero. It's just going to be very, very small. So the astronaut is firstly still in orbit. Still in orbit. Right? And because they are in orbit, they're going to experience gravity. They're going to experience the gravity, albeit a very small amount. Small value. So actually they are accelerating down to the earth, but at the same time, if they are in the space station at intervals is going to apply its thrusters to move it slightly away. So it's not as simple as just saying that it's weightless. Question 6 says the diagram below shows two identical spheres A and B on insulated stands carrying charges of -4 microcoulombs and +4 microcoulombs respectively. The distance between the centers is 0.4 meters. Question 6.2, calculate the electrostatic force that A exerts on B. So 6.2, F is equal to K, which is 9 times 10 to the 9, Q1, which is 4 times 10 to the power minus 6, Q2 is also 4 times 10 to the minus 6. Remember, for this formula, we do not include the sign. Divided by r squared, 0.4 squared. And that gives us an answer of 0.9 newtons. And they didn't ask for the magnitude, they asked for the actual force, so we need to give a direction. So the force that A exerts on B. So if we are at B, A is going to want to pull it to the left. Question 6.3, draw the electric field pattern due to the two spheres. Well, A is going to have a negative charge and B is going to have a positive charge. The arrows go from the positive toward the negative, and so they should overlap and interact like this. And here, out, out, and then out. And that's basically it. Sphere B is now replaced by a third sphere, sphere C, carrying a charge of -9 microcoulombs. P is a point along the line joining the centers of the spheres as shown in the diagram below. Define the electric field at a point. Okay, that's fine. Question 6.5. If the net electric field at point P is 0, calculate the distance between point P and the center of sphere A. Okay, so what we'll do here is we're going to say that the electric field due to A plus the electric field due to C is going to equal 0. And the reason why we're doing this is because if we had to draw a field diagram, not a force diagram, showing the fields acting at P, well, it's going to look like this. So if you imagine that P is a positive charge, which generally we do, P is going to be pulled toward C. So that way, so that's going to be the electric field due to C. And it's also going to be pulled to the left because A is also negatively charged. So that's going to be the electric field due to A. Now, because the net electric field is 0, it means that the electric field at C and the electric field at A is going to equal to one another. So you could say this, or you could say the electric field at A is equal to the electric field at C, or due to C and due to A rather. Now let's go with this one, and now we can substitute. So we know that electric field is kq over r squared. So k is 9 times 10 to the power 9. The charge of A is 4 times 10 to the power minus 6 divided by, let's call the distance from A to P, let's call that x. So it's going to be divided by x squared. And that's going to equal 9 times 10 to the power 9. C has a charge of 9 times 10 to the minus 6. And divided by, if that's x, that's going to be 0.4 minus x. So here we're going to have 0.4 minus x all squared. And now we can solve for x. So we'll say that x is equal to 0. You can use your calculator, shift solve function. X is equal to 0.16 meters. And that is the distance that they want. They want the distance between A and P. Now let's take a look at question number 7. The battery in the circuit diagram below has an internal resistance R. The ammeters and connecting wires have negligible resistance. Both switches, S1 and S2, are closed. The reading on the voltmeter V2 is 18 volts. So this is 18 volts. And the power dissipated by resistor R is 12 watts. So that's 12 watts. Okay. Question 7.1. Calculate the resistance of resistor R. If you look at the information that we know the voltage and we know the power. So we can use the formula P is equal to V squared over R. So since we want R, we just have to substitute. We're going to have 12 is equal to 18 squared divided by R. R is equal to 27 ohms. So let's write that in. 27 ohms. 7.1.2 says calculate the reading on the ammeter. So the ammeter here is reading the total current. So we have a few options here. One option is calculate the total resistance, and once we calculate the total resistance, we can then calculate current, and then we can calculate the reading on ammeter A. So it is worth 5 marks. So there is going to be a few calculations that need to be done. So I'm actually going to go a different way. I'm actually going to go and calculate the current through this branch here, and then I'm going to go and calculate the current in the upper branch, and I'm going to add them. So for this bottom branch, I know the power, I know the resistance, and I know the voltage. So I'm going to calculate the current through the 27 ohm resistor. That's going to equal V over R. So the voltage is 18 and the resistance is 27. So 18 divided by 27. So 18 divided by 27 is 0.67 ohms. So 0.67 amps. Now for the upper branch, because they are in parallel, the upper branch is also going to be using up 18 volts. So here, so the current through the 12 ohm resistor is going to be V over R as well. So 18 divided by 12, and that's equal to, so 18 divided by 12 is 1.5. So the total, so I total, is going to equal 1.5 plus 0.67, which is equal to 2.17 amperes. Done. Question 7.1.3, calculate the potential difference across the 10 ohm resistor. Well, we know that the 10 ohm resistor is going to be using the total current, or the total current is going to be passing through it. So simply we're going to say V is equal to IR, 2.17 multiplied by 10, which is equal to 21.70 volts. Question 7.2 says, when switch S1 is opened, the reading on voltmeter V1 changes to 41.9 volts. Calculate the internal resistance of the battery. So the 41.9 is actually going to be the EMF. Because remember, the reading on the voltmeter that's connected to the terminals of the battery when the switch is open or when no current is flowing through the circuit is known as the EMF. So the EMF is that. Now, if they want to know the internal resistance, let's use the internal resistance formula. So EMF is equal to I into big R plus small r. The EMF is 41.9. That's equal to the total current, which is 2.17. And then big R is total resistance, which we don't know as yet. So let's go ahead and work that out. The total resistance is going to be, let's work out the parallel first. So we'll say that R parallel is equal to product over sum. So 12 times 27 divided by 12 plus 27. And that's going to equal 8.31 ohms. Then R total is going to equal the, this is for the external circuit, is going to be the parallel plus the series. So that's going to be 18.31. So this is 18.31 plus R. Now we can solve for R. R is going to equal 1 ohm. Now let's take a look at 7.3. 7.3 says switch S2 is now opened while S1 is closed. Okay. Will the reading on the ammeter increase, decrease, or remain the same? Give a reason for your answer. So we are removing a resistor in parallel. So if you remove a resistor in parallel, R total will increase. If R total increases, the total current will decrease. And that's it, 2 marks. Question 7.4, a learner sets up the diagram below to investigate Ohm's law for each of the two resistors X and Y. Ignore the internal resistance of the battery. The following graphs were obtained from the results. State Ohm's law. Question 7.4.2 says use the graph to determine the resistance of resistor Y. So what does the gradient here give me? Because if it's a straight line, you should be looking at gradient. 7.4.2, you have gradient, which is equal to the change in the y divided by the change in the x. On the y-axis, you have voltage, and on the x-axis, you have current. So R is equal to V over I. So if you work out the gradient of this line, you're going to get the resistance. So simple, work out the gradient. So to work out the gradient, we need two coordinates. I'm going to say that that is 12, and I'm going to go with that as 0.9. So I'm going to use 12 divided by 0.9. You can do y2 minus y1 over x2 minus x1. It's going to be the same thing because the other coordinate is 0, 0. So that's going to give us 13,33 ohms. Question 7.4.3 says, resistors X and Y are connected in series to a battery in a circuit. Which resistor X or Y will be more suitable to boil the same mass of water at a faster rate in an electric kettle? Give a reason for your answer. So here, what we're looking for is which one is going to have a better power output. Because remember, to boil water, you need power, you need energy. So we are looking for the resistor with a higher power output. So if you look at the formulas for power, well, power is going to equal I squared R. So the higher the resistance, remember the current going through them is the same because they're in series. The higher the resistance, the higher the power. So because Y has a steeper gradient, Y is going to have a higher resistance, and so it's going to have a greater power output. So here we're going to answer that Y would be more suitable because P is equal to I squared R. Since they're in series, we're using this formula. And then the higher the resistance, power is going to be directly proportional to resistance. So Y is more suitable. Question 8, the last question in the paper. In the diagram below, the north pole of a bar magnet is being used to pushed into a coil. The induced EMF in the coil is recorded by the galvanometer. When the bar magnet moves in and out of the coil and the bar magnet exert a force on each other. Is this a mechanical force or a magnetic force? It is a magnetic force. Question 8.2 state the direction of the induced current through the galvanometer. Is it A to B or is it B to A? Now here you need to imagine what's going on. So when the magnet is being pushed into the coil or into the solenoid is going to want to repel it. And so the solenoid is going to create its own, it's going to induce its own magnetic field, and its own magnetic field will induce a current. So the magnetic field for the solenoid is going to look like this. So NS, because remember, north will repel north. So in doing that, if you use your right hand here, you'll notice that your thumb points in the direction of the magnetic field. So we're pointing it to the north. We're pointing it north. So your thumb should be pointing left, and the direction of your forefingers that's left are going to be pointing in the direction of the current. So the current is going to be pointing upward at the front of the solenoid. So up here, like so. Now if you follow the wire, it's going to go up here. It's going to go down the back, and it's going to go from A to B. So answer here from A to B. Question 8.3, write down the reading on the galvanometer when the bar magnet is at rest in the coil. So there's no relative movement, so it's going to be 0. So question 8.4.1, question 8.4 says a coil is made up of 100 turns of an insulated copper wire, each having a circular area of that. The coil is placed in a uniform magnetic field of that in such a way that the angle between the magnetic field and the normal to the coil is 30 degrees. The coil is then rotated so that the angle changes to 70 degrees in 0.2 seconds. Question 8.4.2, calculate the magnitude of the induced EMF. Now, we can use the formula here. 8.4.2, we can use the formula EMF is equal to minus n multiplied by delta phi divided by delta t. Now remember that delta phi is going to equal the final minus the initial, and it's going to be BA cos theta. So minus n, so minus the number of turns on the coil is 100. and then into, let's use a square bracket here. So the final is going to be BA cos theta. So the magnetic field is 3,9 times 10 to the power minus 4 times the area, 4.8 times 10 to the minus 4 as well. And then the final angle is 70 degrees. So times cos of 70 degrees. Then minus 3.9 times 10 to the minus 4 times 4.8 times 10 to the minus 4 times cos of the initial angle, which is cos of 30 degrees. And we close that. And that's all divided by the time in which this occurred, which is 0.2 seconds. That means the EMF is equal to 4.9 times 10 to the minus 5 volts. Very, very small voltage. Question 8.4.3, calculate the induced current in the coil if it has an effective resistance of 2 ohms. So I is equal to V over R. The voltage is 4.9 times 10 to the minus 5 divided by the resistance. They tell us is 2. And so that's going to equal 2.45 times 10 to the minus 5 amperes. That's the whole paper. If you stuck around, thanks so much for watching. Don't forget to leave a like, share this video with your friends, and subscribe for more. I'm going to be working on more full exam past papers, so let me know what you want me to do next, and I'll see you in the next one. Bye-bye.